Imagine trying to track a breakdancer doing a backflip in a crowded room. Now imagine teaching a computer to do it without losing sight of who is who. Let's dive into how AI is solving the ultimate visual shell game. Welcome to our podcast, Artificial Intelligence, papers and concepts curated by Dr. Satya Malik and narrated using AI-generated voices.
It really is a wild concept when you stop and think about it.
Oh, absolutely. And, that's the mission for today's deep dive. We're getting into this breakthrough paper called Observation-Centric SORT, Rethinking SORT for Robust Multi-Object Tracking.
Right. Observation-centric. That's the key phrase here.
Exactly, because the whole point of this is figuring out how AI can actually reliably track multiple objects. I mean, we're talking people, cars, whatever.
Yeah, especially when they temporarily disappear behind something or when they move in completely unpredictable ways.
Which happens constantly in the real world. And, addressing you listening right now, whether you're interested in how autonomous vehicles track pedestrians so they don't crash, or how sports analytics track players in a super chaotic basketball game.
Yeah.
This deep dive is going to reveal the mechanics right behind the curtain.
Yeah, it really pulls back the curtain on why the older systems just kind of fall apart in that chaos.
Right. And before we really get into the weeds of how this new method fixes those older systems.
The baseline.
Exactly, the baseline. But real quick, this podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
Awesome. So getting back to the baseline.
Okay, let's unpack this because the paper talks a lot about traditional SORT, right? And the Kalman filter. How does all that actually work?
Okay, so SORT stands for Simple Online and Real-Time Tracking. And the engine driving it is the Kalman filter.
It's basically just a math formula,
Yeah.
right?
Exactly. It's a recursive algorithm. And it mostly does two things. It makes a prediction, and then it does a measurement update.
Okay, wait, walk me through that prediction part. What is it actually predicting?
Well, it looks at an object, say a person on a street, and it draws a bounding box around them.
Like an invisible rectangle on the screen.
Right, an invisible rectangle. It calculates where that box is, how big it is, and its velocity, like how fast it's moving across the frame.
Okay.
And then for the very next frame of the video, it just assumes the person kept moving at that exact same speed in that exact same direction. It predicts where the box should be.
Ah, so it's relying heavily on what the paper calls the linear motion assumption.
Yes, it assumes movement is a straight line, which, to be fair, in high frame rate video where you have just milliseconds between frames.
People don't usually teleport in a millisecond.
Exactly. It works fine.
Okay, I think of it like it's like watching a car enter a tunnel, right?
Oh, that's a good analogy.
Yeah, like you see a car driving dead straight at 60 miles per hour right before it hits the dark tunnel. So your brain just naturally assumes it keeps driving straight at that same speed.
Right.
But if that tunnel is really long and the car actually, I don't know, swerves or hits the brakes in the dark, your mental prediction of where it is when it comes out the other side is going to be completely wrong.
That is exactly what happens to the Kalman filter when an object gets occluded. When a person walks behind a bus, the AI loses its visual measurement.
So what does it do? Does it just panic?
What's fascinating here is how it handles that blind spot. Instead of panicking, it just does a dummy update.
A dummy update.
Yeah. Since it doesn't have a real measurement from the camera, it just takes its own prediction, its own guess, and treats it like it's a hard fact.
Wait, it trusts its own imagination over reality?
Exactly. It feeds its guess back into the loop as if it were real data. And that causes what the researchers call temporal error magnification.
Oh, because if the first guess is even slightly off,
The next guess is based on that bad guess, and the next one is even worse.
it just snowballs.
Right. The errors compound. By the time the person steps out from behind the bus, the AI's predicted bounding box has drifted so far away from the actual person that the system just...
It drops them. It thinks it's a completely new person.
Exactly. It assigns a brand new ID number. The track is broken. It's fundamentally estimation-centric. It trusts its flawed math more than anything else.
Okay, so if the old system trusts its flawed imagination way too much, the solution has to be, forcing it to look at reality.
Yes. That's the entire philosophy of OC SORT, observation-centric tracking.
So how do the researchers actually solve this snowballing error?
They build a tool called ORU, which stands for Observation-Centric Reupdate.
Reupdate, okay.
Yeah, so when the AI loses a track, the person goes behind the bus and then finds them again. It doesn't just keep guessing forward.
Right.
It pauses. And it looks backward over that lost period. It creates a virtual trajectory to backcheck the math.
Okay, wait, let me stop you there. Wait, if the AI couldn't see the object during that time, how does creating a virtual trajectory make it any better? Isn't it just guessing again?
It sounds like it, right? But it's actually a completely different mathematical approach. It's interpolation instead of extrapolation.
Interpolation.
Yeah. The old way, extrapolation, is a blind guess into the future with no endpoint. But with ORU, the AI now has two pieces of hard evidence.
The moment it lost them and the moment it found them again.
Exactly. It anchors its math on that hard evidence, the exact point the object was last seen and the exact point it reappeared.
Oh, wow.
By interpolating between those two real observations, it retroactively fixes all the accumulated errors in the filter's parameters.
So it cleans up its own mess.
Yes, it fixes the historical data so that on the very next frame, it doesn't just instantly lose the person again.
That makes so much sense. It's drawing a line between two facts instead of just throwing a dart in the dark.
Exactly, and that handles the long occlusions. But they also had to deal with the messy frame-by-frame noise.
Like when the camera shakes.
Yeah.
Or the video quality is just bad.
Right. If you just look frame to frame, the velocity looks super erratic. So they introduced OCM.
Observation-Centric Moment.
You got it. Instead of trusting the noisy instant velocity guess, OCM looks at the real observations over a slightly longer period, say 3 frames,
Okay.
and it calculates the consistent movement direction. It builds that true momentum into the matching process.
So it smooths out the jitters by looking at the bigger picture.
Exactly. And there's one more piece, OCR, observation-centric recovery.
What's that for?
Short stops. Like, if someone stops abruptly or disappears behind a thin pole for just a fraction of a second.
Oh, because the AI's prediction would just keep flying forward while the person stopped.
Right. So when the match fails, OCR just says, hey, forget the prediction for a second. Let's just check the exact spot we last actually saw them.
Just in case they stay totally still.
Exactly. It's a really simple, elegant safety net.
Okay, so we've got the theory down. Here's where it gets really interesting, though. The real-world testing.
Oh, the data sets they used are brutal.
Right. Like looking at the paper's images, they talk about the dance track challenge.
Yes, dance track is notorious.
I mean, the image shows a dancer executing a literal backflip in a crowd of other dancers dressed exactly the same.
A backflip is the ultimate nightmare for that linear motion assumption we talked about earlier.
Right, because for a split second, the person is entirely upside down. Their vertical bounding box becomes completely horizontal.
And traditional SORT just collapses there. It encounters an ID switch mid-flip. It literally thinks the dancer landing is a new person.
But OC sort, it holds onto that ID the entire time. The tracking ID hovers right over the dancer's head, flawlessly all the way through the flip.
Because it's not freaking out over the bounding box shape changing. It's relying on the actual observational momentum.
It's nuts. And it didn't just beat the baseline in dancing, right?
Not at all. It set state-of-the-art records across the board. They tested it on MOT-17 and MOT-20.
Which are the pedestrian ones.
Yeah, lightly crowded, pedestrian streets. Think like a packed Tokyo crosswalk, just bodies constantly overlapping.
Total chaos.
Total chaos.
Yeah.
And it also crushed it on Kitty Eye, which is a data set for autonomous driving, tracking cars and pedestrians from a moving vehicle.
Oh, so the camera itself is moving, too.
Exactly. And my favorite part is how well it works for tracking specific body parts. Like just tracking heads in a dense, crowded stadium.
Which has to be incredibly hard because everyone's head looks basically the same from far away.
And they block each other constantly. But OC Sort handles it beautifully.
So what does this all mean? I mean, usually when an AI model gets this robust, it's because someone threw a math supercomputer at it.
Right. Usually you just bolt on a giant, heavy neural network to handle the math.
Yeah.
But the most staggering part of this paper isn't just the accuracy, it's the speed.
How fast?
Because it remains simple, online, and real-time. It runs at over 700 frames per second.
700?
Yep. On a single standard CPU.
Wow. Not even a high-end graphics card.
No heavy GPUs required. It provides extreme robustness just by fixing the math, not by adding processing weight.
That is incredible. I mean, it means you can put this tech on cheap, edge computing devices. Like a basic traffic camera could run this without needing a server farm.
Exactly. It totally lowers the barrier to entry for robust tracking.
It's such an elegant solution, just forcing the AI to look at the evidence instead of its own imagination.
It really is. And, you know, it leaves us with something pretty intense to think about.
Oh.
Yeah. I mean, if algorithms like OC-sort can now flawlessly connect the dots of a person's path, even when they move erratically, or disappear behind obstacles in a massive, chaotic crowd,
Right.
what does that actually mean for the future of anonymity in public spaces?
Oh, wow.
If we can literally no longer get lost in the crowd because the math is just too good, how do we balance this incredible technological safety net with our own personal privacy?
That is a heavy thought to end on. It's a completely different world now. Thank you for listening. And please subscribe to join us for more deep dives into the cutting edge of AI.